Total non-negativity has applications in many different areas of math and even outside of math. So I'd like to mention one in chemistry. Now, chemists use graphs called hexagonal systems. To represent molecules involving carbon and hydrogen. So one hexagon like this represents 6 carbon atoms with alternating single and double bonds, and then some hydrogen atoms sticking off the side. Actually, the average of that and this, well, let me leave this hexagon alone because this one is representing that molecule, and so I put the double bonds and single bonds in opposite places here. So this hexagon really represents the average of these two. This is also written as a circle in there to mean that the double bonds don't really happen in these places or in those places. The electrons are somehow distributed around. Now also we could have the hexagonal system isn't necessarily just one hexagon, it could be several. And the hexagons can share edges. So this represents 2 hexagons of carbon atoms. And I won't bother putting in the single and double bonds. And then hydrogens coming off of every vertex. So that what we see is a graph where every carbon has degree 3. This one already has 3 neighbors, so it doesn't get a hydrogen. And this one already has 3 neighbors, so it doesn't get a hydrogen. So, well, it's cumbersome to draw all these C's and H's and edges, so chemists usually just draw the hexagonal system. Now the molecule that we get is called a benzenoid hydrocarbon molecule. So the resulting molecules, if they exist, are called benzenoid hydrocarbon molecules. No, I said if they exist because it's possible to draw hexagons in the plane in a way that the molecule can't exist. Not every hexagonal system has a real molecule associated to it. So the question is, given a hexagonal system, is there a benzenoid hydrocarbon molecule that has that system as its skeleton. So we'll say this hexagonal system is the skeleton of that molecule. So for example, let me put up two hexagonal systems that look very similar and tell you how we distinguish which one could actually be a molecule and which one's not. So let's have a row of 7 hexagons. Let me put 2 hexagons above it in that position and that position, and 2 hexagons below it in this position and that position. Now let me draw a similar molecule or a potential molecule with 7 hexagons. And then I'll put hexagons above it in almost the same places. Now I'm going to skip 2 and put another one here. And then on the bottom they're going to be exactly the same. So we have each of these hexagonal systems, and we're wondering, is there a molecule that looks like that? It turns out that the way to decide is to think of these as a planar network, with the peaks being sources and then the valleys on the bottom being sinks. So we have sources on top, sinks below. Sources are the peaks and the sinks are the valleys. So it turns out that there is a molecule if we can find a non-intersecting path family from all the peaks on top to all the valleys below, all the sources to all the sinks. Alright, so let's see if we can find non-intersecting path families for these hexagonal systems. So let's make one path go that way. And then from this vertex, I guess we have to go there. Oh, looks like this one's going to be stuck. I don't see how we can get, all the edges are oriented down. So if we just go down, we're not going to be able to get from this source to that sink. I think we can do all the other ones. We can't get from this one to that one, so the answer is no here. Now let's try for the bottom hexagonal system. Yeah, we can do it. So there is a benzenoid hydrocarbon molecule that has this skeleton, but there's none that has that skeleton. No, I said the molecule can exist if there's a non-intersecting path family. Not that it certainly exists, because, so if we just had a row of hexagons, then we've got a sort of an easy non-intersecting path family from all the peaks to all the valleys. For a row of 1 hexagon, 2 hexagons, 3 hexagons, 4 hexagons, etc. For any natural number of hexagons, I guess we could do it. But there's infinitely many molecules like that, and there's only finitely many molecules in the universe. So I guess not all of those exist. But the molecule can exist if there's a non-intersecting path family from peaks to valleys, and it cannot exist if there's no non-intersecting path family. And just one more note about this. The number of non-intersecting path families gives some information about the energy of the molecule. I don't know enough chemistry to tell you what that information is, but what I got from the papers I have is that there's some information about the energy of the molecule. Of course, the number of non-intersecting path families is the determinant of the path matrix. And aside from this chemical application, maybe I'll just mention a couple other applications. So I think Gontmacher was the first one to introduce these matrices in the literature. And that was maybe 1940 or earlier. 30s. So he used totally non-negative matrices to study oscillations in mechanical systems. And let's see, Carlin and McGregor, who I think were the first ones to publish Lindström's lemma, long before Lindström, were studying continuous time Markov chains. Which they used to model populations of organisms. And 3, Lindström in 71 was studying matroids when these came up in his work. There are many others, but I think those are 3 that you should know. The end.